Hey guys, my name is IBM and I welcome you to my YouTube channel. Do not forget to subscribe and share the videos with your friends. Don't forget we are dealing with astrophysics and cosmology, and I think this is going to be lesson number 2. So without wasting time, I just want to remind you that we are dealing with the Cambridge International Education, or the CIE. This is physics 97802, and this is so just to remind you the topics we expect to be to this is the first outline, circulation, gravitation, ambient gases, temperature, thermodynamics, simple multiplication, oscillations, electric fields, magnetic fields, and electromagnetic induction, capacitancy, alternating currents, nuclear physics, quantum physics, astrophysics and cosmology, and medical physics. Do not forget we are currently dealing with astrophysics and cosmology, having done nuclear physics. So here we are on astrophysics and cosmology. Do not forget to subscribe. Do not forget to share the videos. And this is going to be lesson number 2. So just to give you a highlight of what we should expect in lesson number 2, the first thing we shall start with in lesson number 2 is going to be surface temperature of a star. Remember in lesson number 1, we explored the light year, we explored the concepts of luminosity. In lesson number 1, we explored the concepts of radiant flux intensity. And I think we concluded lesson number 1 with the inverse square law and with the several examples. So in lesson 2, I want us to begin with the surface temperature of a star. And under this part, we are going to explore 4 important areas, which include, we shall discuss Wien's displacement law. We shall talk about the black body or black body radiation. We shall talk about the features of a displacement graph that is under the Wien's displacement law, and we shall also talk about Stefan Boltzmann's law. When these 4 areas are covered, I think lesson number 2 will be done. So to begin with, let's start with Wien's displacement law. So around 1893, a German physicist in the name of Wilhelm Wien found experimentally that there is a relationship between a wavelength of light emitted by an object and the surface temperature of the object. In other words, Wien experimentally showed that there is a certain relationship between wavelength of the peak intensity of radiations emitted by a body, which we later on refer to as a black body, and then the surface temperature of the body, as we shall see later on. So this relationship is what we today call Wien's displacement law. So there is a link between the observed wavelength of light and the surface temperature of the body. And when you look at objects, many times, if you hit a metallic object on a burning flame or a Bunsen flame, you may notice initially the object turning maybe bluish. It starts changing color, bluish, red, orange, white, and so on and so forth. So as the temperatures of the object change, the color of the object also change. Remember, each of these colors represent a wavelength, or it represents a frequency. So it's like there's a relationship between the temperature and wavelength, or there's a relationship between temperature and the frequency of radiations coming from an object which is being heated. So the hottest stars are normally bluish or white in color, or they are bluish white in color. The hottest stars are normally bluish white in color. So remember, according to Wien's experiment, there is a relationship, or there is a link between the wavelength and the temperature. So if the hottest stars are bluish in color, you will remind yourselves of the electromagnetic spectrum, which ranges from the electromagnetic spectrum, which ranges from um, oh, not the electromagnetic spectrum, but basically the visible spectrum, which ranges from Richard of York gave birth in vain. So we are saying the hottest stars are bluish white in color. White is almost at the average of all these colors, that is approximately white, but red corresponds to the longest wavelength, and as we move towards blue, it means the wavelength is actually decreasing. So it's like the hottest stars have a smaller wavelength, and the cooler stars are orange or red. They have a deep shade of range of red, or they have brick red color or orange. So red corresponds to the longest wavelength. It's like the cooler stars have a smaller wavelength. So we can start thinking of the fact that the wavelength is somehow inversely proportional to temperature, because we have seen that the hottest stars are bluish white in color, or they are blue in color, and we are seeing that the cooler stars are red in color, which means high wavelength means lower temperature, and low wavelength means high temperature. So it's like there's a relationship between wavelength and temperature, which is an inverse relationship that was established by Wilhelm Wien in 1893. So we are saying cooler stars are a deep shade of red. So the same effect is seen when the temperature of a filament is increased by increasing the current. At first, the filament will glow dull red if you are very observant. When the filament of a lamp is glowing, at first it will be dull red. When it is cooler, when it has just started glowing, and then you will notice that it becomes reddish orange, and eventually, if it is very hot, it will become white, or it turns bluish white as the temperature increases. So these colors are corresponding to wavelengths. That's why we are saying there is a relationship between or there's a link between the wavelength and the temperature of and the surface temperature of an object or of a body. So in memory of Wilhelm Wien, uh, we could say that it was found experimentally by the German physicist in the name of Wilhelm Wien around 1893 that the wavelength at the peak intensity, this is a very important part here, wavelength at maximum intensity or the peak intensity of the spectrum is related to the Kelvin temperature. When I talk about Kelvin temperature, I'm referring to temperature in Kelvin units, or the absolute temperature, or the thermodynamic temperature. It's not temperature in degrees Celsius. So it's like there is a relationship between temperature and wavelength, and we have seen if the hottest stars are bluish white and the cooler stars are red, so it's like the wavelength is inversely proportional to temperature. That's why we are saying that the wavelength, or lambda max, is inversely proportional to temperature. This relationship is going to be called Wien's displacement law. So lambda max is inversely proportional to the absolute temperature, and this relationship is going to be called Wien's displacement law. So this is the relationship, or it is the link between the temperature and wavelength at maximum or at peak intensity. So the relationship lambda max inversely proportional to the absolute temperature is called Wien's displacement law. So many times when we are asked to state Wien's displacement law, we can write lambda max inversely proportional to T, but we have to define what lambda max stands for. That is wavelength at peak intensity, and T is the Kelvin temperature, or the absolute temperature. So we are saying lambda max times T is therefore going to be equal to a constant. That is, if I cross multiply both sides by T, it means lambda max, and I remove the proportionality sign, so it means lambda max is going to be simply equal to a constant. So lambda is wavelength at the peak intensity. This is the very important thing. It is not maximum wavelength, but it is wavelength at peak intensity of the star. The wavelength at peak intensity of the radiation which is emitted from the star. And remember, I've just mentioned that T should be the thermodynamic temperature at the surface of the star. So that is what we call Wien's displacement law. So precisely, we can put this in words and say that the wavelength at which maximum intensity of radiation from a black body occurs is inversely proportional to the absolute temperature or to the thermodynamic temperature. This is what we call Wien's displacement law. The wavelength at which maximum intensity of radiation from a black body occurs is inversely proportional to its thermodynamic temperature. Now, the value of the constant, we have said lambda max times T equals to a constant. Experiments have shown that the value of this constant is about 2.9 times 10 to the power of minus 3. Because lambda is in meters and temperature is in Kelvin, the unit is meter Kelvin. Now, this constant, you will not find it in the list of constants if you are doing, even if you're doing OCR or you're doing Cambridge, you don't find this constant in the unit of constants, but many times when you multiply the temperature and it's the wavelength at maximum intensity, the product will be approximately 2.9 times 10 to the power of minus 3 meter Kelvin. This is what we call Wien's constant. Now, I have mentioned the black body, and many of you may be asking yourselves, what is a black body? In your physics of IGCSE thermophysics, you must have mentioned a black body where you were looking at heat transfer, and you were talking about radiation, where heat is being transferred by electromagnetic waves. And you realize that there are those objects which absorb all radiations falling on them without reflecting any. They were very perfect or very good absorbers, and they were also very good emitters, but they were very poor reflectors. So a black body is an object which absorbs all radiations, all wavelengths incident on it without reflecting any, but then it emits all the wavelength. In other words, absorbs all wavelength incident on it, but without reflecting, but then it emits. Now, many times we confuse emit and reflect. These two are not the same. Reflect means there was no absorption, but emitting means it is coming from within the body, so there was absorption. So black body is an object which absorbs all the radiations falling on it without reflecting any, but it emits radiations in a continuous spectrum, or in a continuous range of wavelengths, as we shall mention later on. So that is what we call Wien's displacement law. So a hot object such as a star can be modeled to be a black body. Having mentioned what a black body is, a hot object such as a star may be mentioned to be, maybe modeled to be what to be called a black body, or maybe modeled as a black body. Now, a black body does not need to be black in color. A black body may not necessarily be black in color. It could be any object which can absorb all radiations of different wavelengths falling on it without reflecting any. So, an idealized object that absorbs all radiations or all wavelengths of radiations falling on it, and therefore emitting radiations in a whole spectrum. When we talk about a whole spectrum, we are referring to all electromagnetic waves ranging from Richard Reed's mother is visiting Uncle Xavier's garden. Or radiations in all these regions of the electromagnetic spectrum can be emitted by a black body. So that's what we call a black body. It absorbs all radiations falling on it and therefore emits radiations in a whole spectrum of wavelengths. That's what we are calling a black body. It doesn't necessarily need to be black in color. So at equilibrium, a black body has characteristic emission frequency spectrum that depends only on its thermodynamic temperature. In other words, a graph of intensity emitted against wavelength is only going to depend on the absolute temperature or on the thermodynamic temperature. For example, At normal temperature, we know that, or we are not aware of these electromagnetic radiations because of its low intensity. Of course, 300 Kelvin is approximately, if I subtract 273, this is approximately, I think this is approximately 27 degrees Celsius. At 27 degrees Celsius, which is maybe room temperature somewhere, we may not see most of these radiations which are emitted from a black hole. That's why when you are seated somewhere, you may not know that you are emitting radiations from your body. But because you are acting as a black body, radiations are leaving your body. But because the temperature is low, the wavelength is high, and it is not in the visible spectrum, so we cannot see these radiations coming from your body. So that's why we are not aware of them, because of their low intensity. However, if we continue heating the body, if the temperature of the body is high, the black body now begins to glow with thermal radiation. In other words, now it begins to glow, turning to the wavelengths whose colors are visible to our eyes. That's why at temperatures, for example, above 2000 Kelvin, at very high temperatures, objects start glowing yellowish or whitish. Now we are in what we call the visible spectrum. So when the temperature was low, the wavelength was high, we had not reached the visible spectrum, so we may not be aware of such radiations or electromagnetic waves coming from a black body because of the low intensity and the high wavelength. But as temperatures increase, the wavelength of radiations coming from the body decreases, and the wavelength tends towards the visible region where we have the 7 colors ranging from red to violet, which our eyes can easily detect. So at high temperatures, say temperatures above 2000 Kelvin, objects will start glowing. You see yellow, you see whitish in color, and so on and so forth, because now the temperatures are extremely, extremely high. A simple demonstration of this can be illustrated here. So I want to use this slide to demonstrate for you Wayne's displacement law. So in this demonstration here, a metallic object is being heated. And if you look at the color here, around this region here, if you look at the color of the object, that is the magnified part of the object, you notice that as the temperature increases, as demonstrated here, as the temperature increases, you notice that as the temperature increases, the color of the metallic object starts changing. But at low temperatures, the metallic object first becomes red, then orange, yellow, and so on and so forth, and as we see in this demonstration here. But as it heats up, you just look at how how the color changes when the temperature increases. So let's replace the burning flame with a more powerful flame. So you notice that at the extreme end, where the temperature is still low, it is around red, orange, and so on and so forth. But as temperatures increase, the color changes, and we have now reached almost white because the temperature is extremely high. It is around 1200. So it tends towards white because the temperature is increasing. And remember, white is almost the average of all the 7 colors. But of course, after white, we would be tending towards blue and so on and so forth, because the wavelength is actually decreasing as the temperature increases. So temperature, or I mean the wavelength at maximum intensity of a black body is inversely proportional to the absolute temperature. And as the object cools down, we move backwards. We move backwards because the temperature is decreasing. The wavelength now starts increasing, where we move from white, yellow, we move towards orange, red, and so on and so forth, until when the temperature is too low, then we don't see any radiations coming from the object. Therefore, we are saying that the wavelength at maximum intensity is inversely proportional to the absolute temperature, or the Kelvin temperature of the object. That is Wayne's displacement law. The wavelength at maximum intensity of radiations coming from the body is inversely proportional to the absolute temperature. That is Wien's displacement law. But remember I said that at equilibrium temperature, a black body has a characteristic emission frequency spectrum or wavelength spectrum that depends only on its thermodynamic temperature, and I have demonstrated this spectrum here. Measured spectra of wavelengths and frequencies emitted by a black body at three different temperatures. I've demonstrated three different temperatures and I'll try to explain them here. So at low temperature, the first graph where temperature is T1, that is low temperature, we notice that the peak is somewhere here. The peak intensity is somewhere there. And the wavelength at peak intensity is a value which is around here. So the temperature of the body is relatively low and the peak intensity is somewhere here, and the wavelength corresponding to that, which I may call lambda 1, is somewhere there. Then let's consider the same object being heated. The wavelength was the wavelength was high, and maybe it was beyond or it was out of the visible spectrum. But as the temperature increases to T2, you notice that the peak is now at this point here, which corresponds to a relatively shorter wavelength. So this is lambda 2. Lambda 2 is somewhere here. And the intensity is higher. So the peak corresponds to a shorter wavelength. Note that we are turning towards shorter wavelengths, so we are turning towards the visual spectrum in the electromagnetic spectrum because Reed's mother is visiting Uncle Xavier's garden. So at longer wavelengths or at higher wavelengths, we are this side of the spectrum of the visible spectrum. So here we have red up to violet. So this is infrared. So as we continue heating so that the temperature is now T2, that is a temperature which is now even higher, we notice that the wavelength is somewhere here. So this is going to be lambda 3 at higher temperature, where the peak intensity is somewhere here. So what is happening to the peak? It means we are tending towards the visible spectrum here. Because if we were to increase temperature further beyond T3, we would now reach this region here. We would now tend to this region. After the infrared, we would now tend to this region here, which would be the visual spectrum here. So now radiations emitted will have wavelengths which will be in this region here. Therefore, we shall start seeing colors. After infrared, you may start seeing now red, you see orange, you see yellow, you see green, blue. You may not see green and blue, but you may see white, which could be the average there. And if you continue heating and heating, we may end up to violet because the wavelength is decreasing as the temperature increases. So this is called the characteristic graph, which shows the intensity against wavelength of a black body whose temperature is increasing. Note that I've placed the wavelength at the bottom and I've placed the frequency at the top. You may have a graph of just intensity against the frequency, and you will see smaller values of frequency. You will see smaller values of frequency this side towards the right hand side because wavelength is inversely proportional to frequency. So as temperatures increase, the wavelength at which the maximum intensity coming from a black body or an object occurs is inversely proportional to the absolute temperature. As temperature increases, the wavelength at which the peak intensity occurs is inversely proportional to the absolute temperature, and that's what we called Wien's displacement law. So to explain these peaks or to explain this graph, I try to explain this graph. You should be able to sketch those three peaks. To explain this graph, we have said the radiation emitted is a continuous range of wavelengths. That's why we have seen a curve. We have seen a continuous distribution of wavelengths It is a curve, continuous distribution of wavelengths ranging from high wavelengths to low wavelengths. And the spectrum is a plot of intensity versus wavelength or frequency, since frequency is inversely proportional to wavelength at constant speed. Because here we are considering electromagnetic radiation, which travel the speed of light. So these are the features of the graph that you must have noted. Number one, as the temperature increases, the intensity of every wavelength increases, but the intensity of the shorter wavelengths increases more rapidly. What is the consequence of this? The intensity of shorter wavelengths increases more rapidly, which is equivalent to saying that the peak shifts to shorter wavelength. That's what we have seen from that graph. The peak of the graph shifts to shorter wavelength. So the higher the temperature of a body, the shorter the higher the temperature of the body, the shorter the wavelength at which maximum intensity occurs. The higher the temperature of a body, the shorter the wavelength at which maximum intensity occurs. And I've said this is equivalent to saying the peak shifts towards a shorter wavelength, or the peak shifts towards the vertical axis or the y-axis, which means intensity is inversely proportional to, the wavelength at which maximum intensity occurs is inversely proportional to the absolute temperature. So in a nutshell, I'm saying that the higher the temperature, the greater the intensity of the electromagnetic radiation at each wavelength. But remember, the maximum intensity shifts towards shorter wavelengths. The maximum intensity shifts towards shorter wavelengths as temperature increases. Okay, so you should also have observed, or you should also have observed that all the peak wavelengths are in the infrared region. From the graph that I've drawn above, all the peak wavelengths were in the infrared region. And of course, we can't see infrared. So infrared is indicating relatively lower temperatures from the graph. But I said if we were to continue heating and heating and heating, then we would move from infrared. The next there would be red, where we start now seeing the colors, because red falls in the visible spectrum. So as the temperature increases further and further, the peaks shift from the infrared region towards the visible part of the spectrum, or towards the visible spectrum. And now the appearance or the color of a body is going to depend on the position of the wave of lambda max, or of the position of on the position of the wavelength at which the maximum intensity occurs. The body changes from its color when cold to red hot. That means the wavelength at which maximum intensity is occurring is in the red region of the visible spectrum. If it turns then to yellow, it means the wavelength at maximum intensity is in the yellow region of the visible spectrum. And finally, it turns to white hot, which means the wavelength is now in the middle of the visible spectrum, which is like the average. And finally, if it goes beyond the average, then it turns blue hot. That's why we said the hottest stars are bluish white, and the cooler stars are actually red. So it's like the appearance of an object is depending on where the wavelength or where lambda max falls. So the object starts changing color depending on where the wavelength the wavelength at which maximum intensity is occurring. That's why we are saying initially when you start heating, you will see the object becoming red hot to yellow hot, white hot, and maybe blue, because the wavelength at which maximum intensity occurs continues decreasing as the as the temperature increases. My students normally think that blue hot is cooler than red hot. It's like they think red hot is the hottest, but Red corresponds to the longest wavelength, and according to Wien's displacement law, the wavelength at which maximum intensity occurs is inversely proportional to its absolute temperature. So we don't expect to see blue before red. We expect to see red before blue because red is cooler than blue. So every time, next time you hit or you burn an object, a metallic object, or you place a metallic object on a very violent burning flame, and you first see red, followed by yellow or orange, yellow, white, and so on and so forth. It's only because these colors are correspond to different wavelengths. And as temperature increases, the wavelength at which the maximum intensity occurs decreases. So we only see a body, we only see the color of a body because of where the wavelength at which maximum intensity occurs is falling in that on that graph that we have just demonstrated. For example, let's talk about our sun, the sun. The sun appears yellow. It is not by coincidence that the sun appears yellow. The surface temperature of the sun is approximately 5,800 Kelvin. This gives a wavelength value of about 5 times 10 to the power of minus 7 meters, or about 500 nanometers. Light of this wavelength appears yellow, which is not surprising for the sun. So the wavelength of the sun, the color of the sun is approximately yellow, not by coincidence, because the surface temperature of the sun is about 5,800 Kelvin. And if we consider 5,800 Kelvin using Wien's displacement law, the wavelength of light coming from the sun is approximately, or the wavelength of the radiations around the sun is approximately 500 nanometers, which is actually yellow. So that's why the sun appears yellow, because the wavelength at which maximum intensity, or the wavelength at which peak intensity from the sun occurs at a temperature of 5,800 Kelvin, which corresponds to a wavelength of yellow, as we shall see in calculations. So that is Wien's displacement law. I think I've said a lot about Wien's displacement law, and I think I need to give some examples using this law. Example number 1. Estimate the temperature of the surface of our sun given that the sun emits light whose peak intensity occurs in the visible spectrum of around 500 nanometers. Of course, we know the surface temperature of the sun. It is going to be, or it must be approximately 5,800 Kelvin. Let's try to verify this. According to Wien's displacement law, we know that lambda max times temperature is going to be times absolute temperature is going to be equal to a constant. And of course, this constant, I said you don't need to know this constant. So the examiner will not give you a question where you need to remember this constant. But for this particular question, we know that the constant is 2.9 times 10 to the power of minus 3 mK, or meter Kelvin. So making the temperature the subject, of course, the temperature is going to be equal to the constant, which is 2.9 times 10 to the power of minus 3 divided by the wavelength, which is 500 times 10 to the power of minus 9. I need to call my calculator. Okay, so I have to press the calculator here. So this is going to be, let me say, 2.9 exponent minus 3 divided by 500 exponent minus 9. So this is 5,800. So this is going to be 5,000 800. Of course, the units are kilograms. I mean Kelvin, not kilograms. So it is 5,800. That is going to be the surface temperature of the sun. 5,800 Kelvin. Okay. Example 2. The element of an electric heater has a temperature of 1,150 Kelvin. Calculate the frequency at which the wavelength of the radiation emitted by the element is maximum. We want the frequency at which the wavelength of the radiation emitted by the element is maximum. Okay, so we are just going to use Wien's displacement law. So according to Wien's displacement law, we shall say lambda max. I think this is not good. Lambda max times the temperature T should be equal to a constant. So for now, we shall use the constant as 2.9 times 10 to the power of minus 3. But remember, I said in the exam, you may not need that constant. You may not need to remember that constant. So we want to calculate the frequency at which the wavelength of the radiation emitted by the element is maximum. The frequency, I think not maximum, it is supposed to be minimum. This is not minimum because if the wavelength capture the frequency at which the wavelength of the radiation, it is the wavelength, not the wavelength is maximum, not frequency being maximum. So capture the wavelength. If the wavelength of the radiation emitted by the element is maximum, then we shall say T or lambda max is going to be equal to the constant, which is 2.9 times 10 to the power of minus 3. Then we shall divide this by the temperature, which is going to be 1,150. So that is lambda max. But also remember, from lambda equals to C divided by frequency, we want to find the frequency. So it means C divided by the frequency is going to be equal to 2.9 times 10 to the power of minus 3 divided by 1,150, whichever way you do the algebra. So I get the reciprocal and make F the subject. So F is going to be equal to 1,150 divided by 2.9 times 10 to the power of minus 3, then times C, which C is speed of light, that is 3 times 10 to the power of 8. So I have to check this with my calculator. So this is 1,150 times 3 exponent 8 divided by 2.9 exponent minus 3. So this is giving us a frequency of 1.2 times 10 to the power of 14. It is 1.2 times 2 times 10 to the power of 14. So that is the frequency we are looking for here. Okay, let's see example number 3. The spectrum of of the star Rigel in the constellation of Orion. Of course, we know what a constellation is. That is a pattern of stars in the night sky. That is a constellation. The spectrum of the star Rigel in the constellation of Orion peaks at a wavelength of 263 nanometers. So that is the wavelength at which maximum intensity occurs. While the spectrum of the star Betelgeuse peaks at a wavelength of 828 nanometers. Which of these two stars is cooler, Betelgeuse or Rigel? So I'm going to simply use Wien's displacement law and find out which one is cooler. So according to Wien's displacement law, lambda max, or the lambda at which wavelength at which maximum intensity occurs, or at which the peak occurs, times the temperature T is going to be equal to a constant. Note that this constant is going to be the same for both Rigel and Betelgeuse. So I'm just going to equate the two. So using Rigel, I will say the wavelength of Rigel is 200, and I will not change the units. So I'll simply say 263 nanometers times the temperature of Rigel, I will call it TR, should be equal to the wavelength of Betelgeuse, which is going to be 8 to 8 nanometers, times the temperature of Rigel, which is going to be Betelgeuse, which is going to be, I'm going to call it TB. So I want to find out which one is bigger. I'm going to just make it a fraction, the subject. So I will say, let me say, if I say TR over TB, if the fraction is greater than 1, it means the numerator is bigger than the denominator. If the fraction is less than 1, it means the denominator is bigger than the numerator. So this is going to be equal to 8 to 8 nanometers divided by 263 nanometers. When I look at this fraction, it means Rigel is actually brighter. Rigel has a high. Rigel is going to be. The question is which of the two stars is cooler. So Rigel is going to be hotter because when you look at the fraction, it means the temperature of Rigel is 828 over 263 times the temperature of Betelgeuse. That means Rigel's temperature is higher, is some fraction, or is a certain number bigger than the temperature of Betelgeuse. So I can try to find this fraction, maybe 8 to 8 divided by 263. So this is approximately 3. So it means the temperature of Rigel is approximately 3 times the temperature of Betelgeuse. So I will simply conclude that Rigel is hotter or Betelgeuse is cooler. So Rigel is hotter. It is about 3 times hotter. Or I would say Betelgeuse is cooler. Okay. But even if we don't calculate, you can simply, because our wavelength is inversely proportional to temperature, the one which has the one for which the temperature, the wavelength is higher, it means the temperature is automatically lower. But I just wanted to prove this to you by simple calculation. You could also calculate the temperature of each using Wien's constant and see which one has a higher temperature. But I'm very certain that the temperature of Rigel is going to be almost 3 times the temperature of Betelgeuse. Okay. Example number 4, if it exists. A black body, the Sun, with a surface temperature of 6,000 Kelvin, emits radiation with a wavelength with lambda max equaling 240. Calculate the temperature of Sirius, the hottest star in the northern skies, if the brightest star in the northern skies if lambda max for Cirrus is 72 nanometers. So most of the questions you'll find in the exams look like this, and they would not require you to use the constant which we have been using. So by Wien's displacement law, lambda max times temperature T is equal to a constant. And for that reason, we shall say that I'll just have two equations. For the first one, for the sun, I'll say the wavelength is not known. Calculate the temperature of Cirrus. A black body, the sun with the surface temperature of this emitts radiation. Lambda max is 240, so I'll say 420 nanometers times 6000 Kelvin is equal to a constant. That is equation number one. Then when you consider the Cirrus, its wavelength, lambda max is 72. So I'll say 72 nanometers times the temperature, which is not known, is also equal to the same constant. So because they equal the same constant, I've just equated the two equations. So I'll say T times 72 nanometers should be equal to 420 nanometers times 6000 Kelvin. So what I'm going to do is to divide this by 72 nanometers. So this cancels out, nanometers has cancelled, so my answer is automatically in Kelvin. So T is going to be equal to, I have 6000 times 420 divided by 72. So this is giving me 35,000. Whatever mathematical principle you use, it should lead you to 35,000. So I want you to also note that the temperature used in Wien's law is in Kelvin. That is very important. So many times you should always remember to convert the temperature given from degrees. If it is given in degrees Celsius, you should always remember to convert the temperature to Kelvin before you go ahead and use Wien's displacement law. Okay, I don't know whether I have more examples. Let me check. Let's check. Okay, example 5. When an ion bar is heated at high temperature, it becomes orange, red, and its color progressively shifts towards white and blue as it is heated further. Explain this observation. I think this is an observation that I've already explained. Why do the colors change? Remember, according to Wien's displacement law, the wavelength at which maximum intensity occurs is inversely proportional to temperature. So as the temperature increases, the wavelength at which maximum intensity or at which peak intensity occurs actually decreases. From the visible spectrum, red, Richard of York gave birth in vain. Red corresponds to the longest wavelength. But as temperature increases, the wavelength decreases. Therefore, we immediately see red, orange, because as the temperature increases, the wavelength decreases. So we now see white, because that is the average of all these colors. That is, if we are here at the center, and finally we would see blue. So you would simply tell the examiner that orange red corresponds to the longest wavelength, and according to Wien's displacement law, the wavelength at maximum intensity is inversely proportional to the temperature. So blue has a shorter wavelength than red. Therefore, at extremely high temperature, the object is going to be blue because blue has a shorter wavelength, since the wavelength is inversely proportional to temperature. So in your own words, you can write an explanation to this question. Then example number 6, if it exists. For a temperature of 5,800 Kelvin, the wavelength at peak intensity of electromagnetic radiation is 500. Calculate the surface temperature of a star with wavelength 350 nanometers at peak intensity. Surface temperature of the star. Okay. So using Wayne's displacement law, we know that the wavelength at maximum intensity times temperature is equal to a constant. I want you to note very carefully that this wavelength is not the maximum wavelength. It is instead the wavelength at maximum intensity. So the wavelength at maximum intensity times temperature is equal to a constant according to Wayne's displacement law. So just relating to example number 4, I'll just come up with the two equations and equate them. So for the sun, for a temperature of 5,800 Kelvin, the wavelength is 500 nanometers. So I'll say 500 nanometers times the temperature, which is 5,800 Kelvin. This should be equal to, on the other side, or for the other equation, because the constant is the same, I'm equating the two equations. For the other one, the wavelength is 350 nanometers, and then times the temperature which we want to find as T. So if I make T the subject, for those of you who are doing OCR, remember making a subject is very, very, very important. So this is going to be 500 nanometers times 5,800 Kelvin, and I will divide this by 350 nanometers. Of course, nanometers cancels, which implies my answer is in Kelvin. So I have 500 times 5,800 divided by 350. So this is giving me 8. I'll write 8,000. Let me see how many significant figures. These are two significant figures. So I'll write 8,000. Is it 300? Yes. To two significant figures to be 8,300 Kelvin. So the temperature is 8,300 Kelvin. Okay. Then let's see if there is example number 6. Number 7. We have example number 7. Complete the table below using Wayne's displacement law. You can always pause the videos and try to see if you can answer the questions on your own first. If you can't do that, then it is very unfortunate. So complete the table below using Wayne's displacement law. So I'll use this as the reference. Remember, lambda max times T is going to be equal to a constant. So my constant is going to be 5,800 times 500. That is temperature times lambda max equals to a constant. So for the other temperatures, I will simply say, for example, for the first one, I will say 5,800 times 500 is equal to the wavelength is 820 times temperature, which is T. So I want to come up with an equation. So T is going to be 500 divided by 820 times 5,800. So I'm only going to be changing this one here. Or I will change this one. I think I will change that for the temperature. So I'll press my calculator. 5,800 times 500, this is the constant. Then I will divide this by 820. So this is 3,500 to two significant figures. So I'll put here 3,500 Kelvin. Then here we need to find the wavelength. So I will just make lambda the subject instead. Making lambda the subject, I will say 5,800 times the wavelength, which is 500, equals to lambda times the temperature, which is given as 6100. So it means the wavelength is going to be the constant 5,800 times 500 divided by 6100. So 5,800 times 500 divided by 6100. So that is at two significant figures, it is 480. Then the last one, I will just change the temperature from 6,100 to 700. So this is giving me two significant figures to be 4,100. So that is, I think that is a simple table to complete. Okay, so that was Wayne's displacement law. Then the next thing we need to do is to talk about Stefan Boltzmann's law. Stefan Boltzmann's law. You can't talk about astrophysics without talking about Stefan Boltzmann's law. So I want you to recall, we talked about the luminosity of a star as being the total radiant power which was emitted or which is emitted by a star. However, the luminosity of the star, which we discussed earlier on, we said it doesn't depend just on the surface temperature of the star. Even though we are saying the wavelength at which maximum intensity occurs is inversely proportional to the temperature, I want you also to remember that the luminosity of a star does not only depend on the surface temperature of the star. The luminosity of a star does not only depend on the surface temperature of the star. The total radiant power which an object emits will not only depend on the temperature of the object or the surface temperature of the object. It also depends on how big the object is. That is now what we need to discuss here to arrive at what we call Stefan Boltzmann's law. So the luminosity of a star is depending on also two other factors, and these include, apart from the surface temperature, it will also depend on the radius or the size of the star. A very large star would radiate more power than a very small star. So the total radiant power emitted by the star will not only depend on the temperature, it will also depend on the size of the star. So this relationship, or the relationship between the surface temperature and the radius or the area or the size of the star was investigated by a certain scientist in the name of there were two scientists, I think, in the names of Stefan and Boltzmann. So these scientists were interested in the relationship between the surface temperature, the radius or the size of the star with the luminosity of the star. So to begin with, Stefan was so much interested in the relationship between the temperature and the luminosity of the star. Stefan was so much. What is the other name for Stefan? I think he was called. These were Australian physicists. I think Stefan was called Joseph Stefan. I think, and then the other one is Boltzmann was called Ludwig. So Joseph Stefan was so much interested in the relationship between the luminosity of a star or the luminosity of an object and the surface temperature. And his findings led to the fact, or his findings show that normally the luminosity of an object was always directly proportional to the fourth power of the temperature or of the absolute temperature. On the other hand, Ludwig Boltzmann was interested in the relationship between the luminosity and the size of the star or the size of the object or the area of the star. And these observations also show that normally the luminosity of the star was also always directly proportional to the surface area of the star, or the luminosity or the total radiant power emitted by the object was always directly proportional to the area of the object. So these two people now combined their findings to come up with what we today call Stefan Boltzmann's law. So I said Joseph Stefan was concerned with the relationship between the luminosity and the surface temperature. And his findings show that the rate of radiation, which is the power, which is the luminosity, was proportional to the fourth power of the thermodynamic temperature. In other words, the luminosity, which is the rate of radiation or the power radiated, the total power, radiant power emitted, was directly proportional to the fourth power of the absolute temperature. And then on the other hand, um, Ludwig Boltzmann was interested in the relationship between um, the luminosity and the area or the size of the object. And his findings show that the luminosity, which is the rate of radiation or the power radiated by the star, was always directly proportional to the area of the object. So the luminosity is also directly proportional to the area of the object. So if we combine these two, we can therefore say luminosity is directly proportional to the area and also directly proportional to the object. Remember, the object radiates uniformly in an area surrounding the whole object. That means it radiates in a spherical area around the object. So the area here is a sphere, so we can say luminosity is directly proportional to 4 pi r squared times t to the power of 4, where 4 pi r squared is the area of a spherical envelope around the object, or the area of the spherical envelope, or the spherical area of the object if we consider the star as being spherical. And when we remove the proportionality sign, the luminosity is going to be equal to 4 pi r squared. We must introduce a constant, which constant we are going to call sigma, the Stefan Boltzmann's constant, as we shall discuss later on. So we should be able to state Stefan Boltzmann's law by combining the two. And the law states that the total energy emitted by a black body per unit area per second is proportional to the fourth power of the absolute temperature of the body. Remember, total energy emitted per unit area per second, that is actually the luminosity per unit area per second, is proportional to the fourth power of the absolute temperature. In other words, when I say L divided by A is directly proportional to the fourth power. So L is total energy per second divided by A is proportional to T power 4. The total radiant power emitted is directly proportional to the area and also directly proportional to the fourth power of the thermodynamic temperature. This is what we call Stefan Boltzmann's law. We shall state it in a more simplified way later on. Okay, so we have seen that Ludwig Boltzmann has investigated the relationship between luminosity and area. We have seen that Joseph Stefan has investigated the relationship between luminosity or total radiant power emitted and the temperature, and it was results show that it was always the fourth power, or directly proportional to the fourth power. And therefore, when we combine these findings, we come up with this equation here, which is always given in the list of formula. So the law is going to always be written like this. Many times you'll find Stefan Boltzmann's law written like this in the list of formula, where L refers to the luminosity or the total radiant power. L is the total radiant power, which we call the luminosity of the star. And R is, of course, the radius of the star. And sigma is going to be called Stefan Boltzmann's constant, where experiments later on show that the constant is equal to this. This constant is also given in the list of constants. Then T is the absolute temperature, the surface temperature in Kelvin. It is actually the absolute temperature in Kelvin. It should be absolute surface temperature measured in Kelvin. So we should be able to use this expression here. We should be able to use that expression in calculation. So Joseph Stefan and Ludwig Boltzmann were Australian physicists who made the above observations. I said specifically, Stefan was concerned with the temperature, and his findings showed that the luminosity was directly proportional to the fourth power of the temperature. Ludwig Boltzmann was concerned with the area, and his observations show that luminosity was directly proportional to the area. And we said if luminosity is directly proportional to the area and luminosity is directly proportional to the fourth power, we combine these two expressions to come up with this equation here, where A is the area of a sphere if we assume that stars were spherical in nature. Okay, so in summary, a simpler way of stating Stefan Boltzmann's law, for example, in an exam. So since luminosity is the power emitted by a star, which is the rate at which energy is radiated, instead of using energy radiated per second per unit area, we shall simply say the rate at which an object radiates energy, which is of course the power, is directly proportional to the fourth power, that is T to the power of 4, of its absolute temperature and its surface area. The rate at which an object radiates power, that is the luminosity, is directly proportional to the fourth power of the air of the absolute temperature and also directly proportional to the surface area. Alternatively, we can state the same law in another simpler way. Instead of talking about the rate at which an object radiates energy, which is a long statement, we would simply say the power per unit area radiated by a black body is directly proportional to the fourth power of its thermodynamic temperature. In other words, when I divide L by A, directly proportional to temperature, I will say the power radiated per unit area is directly proportional to the fourth power of the thermodynamic temperature. That is Stefan Boltzmann's law. So you should be able to state this law in words, but normally it is given in the list of formula. You may not even know that is the law. In the list of formula, they will quote for you L being equal to 4 pi r squared sigma T to the power of 4. And it's up to you to know that this is area and this is a constant. So the power radiated is directly proportional to the area and is also directly proportional to the fourth power of the temperature, where sigma is a constant. And that is Stefan Boltzmann's law. A few things or a few takeaways that we need to note from this part of Stefan Boltzmann's law. Number one, shiny surfaces emit less radiation and also absorb little of the radiation that falls upon them. In other words, we know from IGCSE that shiny surfaces mostly reflect. That is very important, especially when we are referring to Wien's displacement law. Number two, when we talk about black and very dark objects, on the other hand, these normally absorb nearly all radiations that falls on them. Dark objects don't need to be black. And for this reason, and for this fact, this is the reason as to why light-colored clothing is usually preferable to dark clothing on a hot day. You mentioned this in IGCSE. because light colored are good reflectors. Light colors are good reflectors, they are poor absorbers. But of course, poor absorbers are also poor emitters. On the other hand, also remember, optics can absorb as many wavelengths as possible. And depending on the color of a solid or depending on the color of the object, you can determine what wavelength it can absorb. For example, if you have a green object, in your mind you know that it is going to reflect green into your eyes, therefore it is going to absorb all the other colors. But if the object is a black object, it is going to absorb all wavelengths. So a solid is the color of the light that it cannot absorb. A solid is the color of the light that it cannot absorb. Because we view objects by what is reflected from the objects into our eyes. So it means an object or a solid is going to appear or is going to have the color of the light that it cannot absorb. A black body absorbs all wavelengths as I have already mentioned, and as it heats up, it emits all wavelengths. That's what we call black body radiation. If you're doing Cambridge, you may not need ideas about black body radiation, but at least you know what we mean by black body radiation or what we mean by a black body. It absorbs all wavelengths incident on it without reflecting any, but again it emits all radiations or all wavelengths, or it emits a range of wavelengths ranging from radio waves to gamma rays. So in a nutshell, I'm saying a good absorber is also a good emitter. And I think this is the statement you mentioned in your IGCSE physics. This is a statement you mentioned in your IGCSE physics. Okay, so how do we estimate the radius of the stars? Now that we have Wayne's displacement law, we now have Stefan Boltzmann's law. I think it is now possible for us to estimate the radius of a given star. It is very possible now to estimate the radius of a given star. Remember, Wayne's displacement law, the wavelength at which maximum intensity occurs times the absolute temperature is equal to a constant. Number two, we have Stefan Boltzmann's law, where the radiant power emitted by a star, the radiant power emitted by a star is directly proportional to the area and also directly proportional to the fourth power of the absolute temperature, which means L equals to 4 pi r squared times sigma times T to the power of 4, if we assume that the star is spherical in nature. So is it now possible for us to estimate the radius of a star? Yes, of course. If we know the luminosity of the star, and using Wayne's displacement law, we can tell the temperature, the surface temperature of the star, because the wavelength of the star can easily be, if we see yellow, we know the wavelength of yellow. So using Wayne's displacement law, we can estimate the surface temperature of the star. And if the luminosity of the star is known, using Stefan Boltzmann's law, we should be able to estimate the radius of the star. So what am I saying here? The radius of a star can be estimated by combining Wayne's displacement law and Stefan Boltzmann's law. Use Wayne's law to find the temperature, because we know that lambda max times T equals to a constant. So use Wayne's law to determine the temperature of the star. Use the inverse square law of flux to find the luminosity. We know that inverse square law tells us that flux is equal to L over 4 pi d squared. If we use the inverse square law to find the luminosity, to find the luminosity L of the star, then the last thing is to use Stefan Boltzmann's law to find the radius of the star, which is L is equal to 4 pi r squared times sigma times T to the power of 4. So if the luminosity of the star is known or has been found using the inverse square law, the wavelength, the surface temperature has been found using Wien's displacement law, then we can find the radius of the star using Stefan Boltzmann's law. Let's try to do an example before we leave this example. Betelgeuse is our nearest red giant star. It has a luminosity of, so the luminosity is known, it has a luminosity of 4.49 times 10 to the power of 31 watts and emits radiation with a peak wavelength of 850 nanometers. Calculate the ratio of the radius of Betelgeuse RB to the radius of the Sun RS. The radius of the Sun is given as 6.95 times 10 to the power of 8 meters. Okay. So remember we said we can use Wien's displacement law to find the surface temperature of the star. And since the luminosity is known, we don't need to use the radiant flux intensity. So using Wien's displacement law, we know that lambda max times T is going to be equal to a constant. Since they have not given us any other condition to eliminate this constant, I will just use 2.9 times 10 to the power of minus 3 meter Kelvin. That is the Wien's displacement constant, or Wien's constant. So it means the temperature of Betelgeuse is going to be equal to lambda max, which is 850. Sorry, it is the constant divided by lambda max. So it will be 2.9 times 10 to the power of minus 3 divided by lambda max, which is 850 times 10 to the power of minus nano, that is minus 9. So 2 exponent minus 3 divided by, 2.9 exponent minus 3 divided by 850 exponent minus 9. So this is approximately 3410 Kelvin to 3 significant figures. And then by Stefan Boltzmann's law, L equals to 4 pi r squared sigma times T to the power of 4. So here I'm going to combine to use this equation for both of them. I'm going to use this equation for both of them. Oh, but anyway, because I don't know this, I don't have the surface temperature of the Sun, I may ignore, I may just, I don't want to assume the surface temperature of the Sun. So since I have the radius of the Sun, I will just find the radius of Betelgeuse and I divide here. So it means the radius R for B is going to be equal to the square root of the luminosity divided by 4 pi sigma T to the power of 4. When I substitute, this is going to be the luminosity, which is 4.49 times 10 to the power of 31 divided by 4 pi times sigma. Sigma is known to be 5.67 times 10 to the power of minus 8. That is Stefan Boltzmann's constant, sigma. Then times T to the power of 4, which is going to be 3410 raised to the power of 4. Okay, so I'll press my calculator. So open brackets 4.49 exponent 31 divide by open the brackets 4 pi into brackets. Okay, let me just say 4 pi times 5.67 exponent minus 8. Let me divide further by 3,410 raised to the power of 4. Then I have to find the square root of the answer. And I'm getting 6.83 times 10 to the power of, since this was given to 3 significant figures, I'll also write that to 3 significant figures, 6.83 times 10 to the power of 11. So this is 6.83 times 10 to the power of 11 meters. So that means the ratio, we want the ratio of the radius of Betelgeuse, that is the ratio RB divided by the radius of the sun, is going to be 6.83 times 10 to the power of 11 divided by 6.95 times 10 to the power of 8. So 6.83 exponent 11 divided by 6.95 exponent 8. So this is approximately 983. So we notice that Betelgeuse is about 1,000 times larger than the sun's radius. About 1,000 times larger than the sun's radius. So it means it is bigger than our sun. Okay. I think that is the end of lesson 2.
What did happen to the last 10? I ran away with my life, fast forward, never turn back again. It's kind of funny that the more we pass time, the more we set the rewind. And I was to get my hands in you, but now I'm seeing